All right, welcome. In this video, I want to start talking about what a proof is and what we can expect when we're asked to give a proof for a particular mathematical statement. And so we're gonna rely a little bit on some of our definitions that we've covered in the last couple of videos on logic and sets. But specifically, we're going to focus in on what is it to be a proof. So let's go ahead and take a look at that. And so I want to start with the definition of a proof. We're going to have a large number of definitions in this video. And I'm going to talk a little bit more about what a definition is coming up in a sort of formal sense. I think most of us probably already know what a definition is, but it plays an important role in a logical sense or in a mathematical sense. So let's start here with our definition of a proof. Okay, now I'm going to give a number of definitions in this series of videos, and when I do, I'm going to try and be consistent, at least with my color scheme here. I'm going to try and use the red to indicate the word that I'm defining, or sometimes phrase. And then I'm going to use sort of the blue here to indicate sort of the key phrase or clause that we're using to define that term. So let's start here. This is a definition of a proof. So it says here, a proof is a valid and sound argument. Okay, and that's sort of the bulk of the definition of what a proof is. I've got some other bits on here. These other bits are actually defining a couple other things for us. It says a proof is a valid and sound argument that establishes the truth of a proposition. So here we are reaching back to our more formal definition. What is a proposition? A proposition, remember, is a type of sentence or a figure of speech that can be true or false. So here we're specifically saying here is a proposition that could be true or false, and the proof establishes its truth. Well, that makes sense. A proof of a statement is trying to show that the statement is true. Okay, so our proof is a valid and sound argument that establishes the truth of a proposition. My red word here in brackets, conclusion, is saying that we name this proposition the conclusion. So the proposition we're trying to prove true is our conclusion. And then it says here that this argument establishes the establishes the proposition from some set of other propositions. Okay, and here we say the assumed proposition. So here we mean prior to the proof, we sort of assume this is our body of knowledge that we already know is true. So rarely are we trying to prove something true in a vacuum where we know nothing true. Okay, instead we usually try and prove things from some point where we've already accepted that some other propositions are true. Maybe they've been proved to us previously or some other reason, and we give a name to these as well. We call these premises. Premises, or if there's a single one, a premise. And then we usually take that set of premises and we try to argue, that's the proof, that's where the proof comes in, argue in a both valid and sound way to the conclusion. Okay, well then, what is this valid and soundness? Here's where we might want to rely on another definition. So here I've got another definition. So I'm going to pull out another one. This is our main definition here, but I've got a couple supporting definitions below. The one here is an argument. So we're going to talk about an argument. We're not defining really what an argument is. I'm going to leave that in the realm of undefined terms. We're going to rely only on our intuition of what an argument is. We could probably formalize it if we wanted to, but for the moment I'm leaving it informal. Instead, what we're trying to define is what would make an argument valid. Okay, here we're saying our argument must be valid and sound. So what makes it valid? Well, here I'm establishing another definition. I'm establishing another definition of the term valid or validity of an argument. And most definitions, as we'll see in a little bit later on, establish an if and only if relationship. So here I've made this very explicit. Here I'm saying an argument is valid if and only if, by definition, everything that comes second. So what is that comes second here? The conclusion is true when the premises are true. So remember, the premises are going to be the set of propositions that we assume are true at the beginning. So, we're going to assume they're true for the sake of argument. Here what we're saying is if they are true, then the conclusion is true. If that actually holds, then we say the argument is valid. We can have invalid arguments where even when our premises are true, the conclusion might not be true. Okay, that would be an invalid argument. We sometimes call these fallacies, where we're led to believe that it might be a valid argument, but it turns out that it's actually invalid, and so we've been convinced of the truth of a proposition in error, with an error in our logic or our reasoning. Okay, so that's one key. So one of the reasons why when we're looking at proofs, we're going to focus in and try and look at their validity is if the proof is not valid, then it might be establishing a false truth, and we don't want to establish false propositions. We only want to establish true propositions. We only want to find the true ones. Okay, so we've got validity down. What about soundness? Well, soundness is a little bit simpler. An argument is sound if the premises are true. That's pretty simple. So we might say your argument is unsound if we think that you're believing in a premise that is not true, even if the rest of the argument is valid, even if your argument would follow. If you happen to believe in a premise that's false, then, well, we can't believe your conclusion either. So our proofs need to be both valid and sound arguments. Okay, so a proof is going to be an argument that needs to be valid. It has this condition and we're going to see in a bit that if we want to make sure that our proof is valid, we can only follow certain rules of inference. So an inference is where we're going to try and infer the truth of a different proposition from some previous set of propositions, our premises. So this inference, we have rules that allow us to make inferences about propositions in the real world, in our systems of logic. And so here, once again, we want to make sure to establish that our proof is valid. We only follow valid rules of inference. Again, more about that coming up. Okay, but even if we follow valid rules of inference, what the second property here is of soundness is saying is we also have to make sure that our premises are true. If we start out with a false premise, often that means we can argue for a lot of other false conclusions. And so we want to eliminate those possibilities. So these two properties, if they are true, then hopefully that means we can believe that the conclusion is true. And let's see if we can prove this. So here, my very first proof that I'm going to offer in this video about proofs is a proof about proofs as well, a little meta here. Okay, so here's the theorem that I'm going to prove now. A theorem is just the name of a proposition. It's a special name for a special kind of proposition. Usually we reserve the name theorem for true propositions. And so now remember, a proposition could be true or false. And some propositions are true sometimes and false other times, depending on certain context. But if we can establish that a proposition is true and is always true, no matter the context, or at least no matter the reasonable context of interpretation, then we might call it a theorem. So a very simple theorem that hopefully all of us believe is true is that 1 + 1 is 2. We might take that as an axiom, more on that in a bit, but hopefully we all take that to be true. So now that we know that is true, we could call it a theorem. Okay, so here's another theorem. If an argument is both valid and sound, then the conclusion is true. Now remember, the purpose of a proof is to establish that a particular proposition is true. So if we want to establish that our conclusion is true, then this theorem is saying that we must have a valid and sound argument. Okay, so let's see if we can argue that that is true. Now follow with me. Hopefully, here's where I'm going to engage what I call our internal logic computers. One of the sort of marvelous things that humans can do, and we can do many, many marvelous things, but probably a foundational or very important one, is we can operate logically. We can operate rationally or with reason. And so our brain is sort of naturally built to do it. It is a computer that has a lot of built-in functionality, but one of those functionality is to reason about propositions logically. And so in fact, Aristotle, who first sort of codified these rules that we follow, was really just reflecting on his own brain, looking in at his own mind, thinking, how do I come to conclusions in my day-to-day life? And then he sort of wrote it down and sort of tried to codify what this was. And that's what we're going to do here in a bit. But let's see if we can follow through this proof. So engage your logical computer right now. See if you can follow as I go through this proof. Your logical computer, if it's following along, should say, aha, that makes sense. Aha, yes, I get that. And if not, well, see if you can fill in the blanks. And again, I'm going to try and fill in the blanks, because one of the key things that we're doing here in this series of videos is we're trying to take what our internal logical computers already do implicitly and make it explicit. Come out with some formal rules that we could follow and check our brain, because every once in a while our brain makes an error, and it would be sure nice if we could double check our brain and say, aha, brain, you can't fool me. Even though you made an error, I see that error and I'm going to skip around it. I'm going to avoid that error. So let's see if we can follow this proof. So let's start out with our proof. Now, this is a special kind of proof where we're going to say if something is true, then something else is true. So usually in this type of proof, which is a very common proof, we start by assuming the beginning part. This is the hypothesis that we're going to assume is going to be true for the sake of our argument. Okay, so say we do have an argument, a potential proof, and let's assume for the sake of argument that it is valid and that it is sound, so that we have already maybe gone through the motions of verifying for ourselves that the argument we've created is both valid and sound. Meaning, by soundness, that its premises are true, and by validity, that if the conclusion is true, or rather the conclusion is true only when the premises are true. So now what we're going to do is take this, we've taken this assumption, something we know is already true. This is our nugget of truth. And what we do in a proof is we take a little nugget of truth and we try and merge it or make it into more than what it already is. So grow it into something more. So we're going to take that a little bit more and we're going to see what can we do about this. Well, often, almost all the time, the first step that we're going to have to do is apply a definition. Now a definition, we've got a couple of them up above here, is a very special kind of proposition that usually we can take to be true without any proof. It's a definition. We just take it to be true and we just assume it is true. So luckily these are freebies. These are free nuggets of truth, if you will. And so we rely heavily on them to get our proof started. So we're going to start here with our definition of validity and our definition of soundness, which we have here. Okay, so by the definition of, I forgot which one I had first, looks like valid. So by the definition of validity, if the premises are true, then the conclusion is true. Now here I've gone and done something. I've done a little bit of logic magic behind the scenes, and I want to make sure it's very clear. I've translated this sentence, the conclusion is true when the premises are true, into this sentence, if the premises are true, then the conclusion is true. Now this is an exercise in logic a little bit, where we want to be careful where we measure, where we want to make sure. Now remember, in our previous video we did this truth table where we took some truth tables. Well, here's where we might want to revisit the idea of a truth table to make sure that these two sentences sort of mean the same thing. Now often what I'll do here, I might read this one slightly different. The conclusion is true only when the premises are true. This, for me, tends to highlight that what we're saying is only when. We're saying then, if the premises are true, then the conclusion is true. That's what the only when means. And so here I've just taken that and translated it down below here. If the premises are true, then the conclusion is true. Now, why did I want to do that? We'll see in a moment. This is going to be important, but this is the more logic ease. Now, I introduced this in a previous video, but what is logic ease? This is where we start changing the way we use our language to emphasize the logical structure of the proposition that we are uttering. Okay, uttering is another way of saying asserting, speaking the sentence. Okay, so here, up above here, this might be a little bit more natural language, and I'll tell you why I wrote it this way up above here, is if I wrote it this way below, I ended up with a double if. And a double if is a very awkward way to phrase things in English. It is a perfectly fine way to phrase things in logic ease, but no one really wants to speak in logic ease because it's complicated and weird, okay? Because we say double ifs and so on, okay? So my mind, my brain, my internal logic computer, specifically my natural English computer, went and translated that naturally. It says what you really mean is the conclusion is true when the premises are true. And most of you who speak English as well, I presume, your internal logic computer already knew what that meant when I said that. And hopefully you all agree with me at this point that it means this. If the premises are true, then the conclusion is true. So here what we've done is we've applied the definition of valid. We've assumed our argument is valid up above here, and then we're saying, well, what do we know about it then, given that we know it's valid? Then we know that if the premises are true, the conclusion must be true. Okay, let's do the same thing for soundness. By the definition of being sound, we know then that our premises are true. And now we're going to use probably the most common rule of inference, the one that we use all the time, every day. Okay, follow it through with me. This sentence says, if the premises are true, then the conclusion is true. The next one says, the premises are true, so what can we conclude? Hopefully we are all saying it together, that the conclusion is true then, right? We've got the first part, what we call the hypothesis or the antecedent of our if-then statement here. This part we know is true. It says here the premises are true. So we know the premises are true. So how does if-then work? Well, if we know the antecedent is true, the consequent or the conclusion must be true. And that's what we're saying here. The conclusion is true. Very meta. All right. So therefore the conclusion is true. Okay. So we're applying, again, this very special rule of inference where that applies to if-then statements. Again, I'll codify that a little bit more in a second. But there we're done our proof. And maybe I'll comment a little bit more about the proof. How do we know we're done the proof? We got to what we were trying to prove. We were trying to argue this bit. Okay, we said if the argument is both valid and sound, then the conclusion is true. So we started at the beginning, we started with an argument that's valid and sound, and we try and get to the end that the conclusion is true, and that's where we got to. Now, we don't usually leave it up to our readers to verify that for us. In a proof, and I assume most of my audience are computer scientists, so I assume a lot of you have done some programming. So I think of a proof a lot like a program. It has a lot of the same parts as a program. A lot of the times we have to define stuff up front. Those are our declarations of variables that we're going to use in our proof. And then it has a logical structure that if you get things out of order, it's going to create sort of proof bugs, if you will. Okay, it's just going to make people cringe when they have to read your proof. So you want to make sure you get them in this logical order. And then the other thing we have is we usually have little signposts or identifiers that help our reader or the compiler, in the case of programming, know what's going on. So in the case of a proof, usually we start the proof with the word proof. Okay, that's pretty straightforward, and a colon, and that usually is, you can think of that as the opening brace or the opening quote saying herein contained is a proof. And so it starts here. Where does it end? It ends with this box symbol, which is a symbol that has been created in sort of formal mathematics to stand in for the phrase QED. And I'm afraid my Greek was never good. I don't know what that actually means in Greek. I could butcher some Greek-like phrase, but I don't really know what it means. I don't really know what the words are, QED, but what it actually means is that which was to be proved. So at the end of the proof, effectively what the little box is saying is therefore, and now I'm finished my proof, and therefore we have proven what we were trying to prove. And so often what I like to think of this as sort of the close bracket or the close brace at the end of the proof, the little punctuation at the end saying, and therefore we are done. Okay, so most proofs are going to be contained in this little proof and then a square box or a QED at the end. Okay, there's other structures of the proof. These two are sort of scope identifiers saying I'm going to do a proof and now I'm done the proof. Well, sometimes in the proof we'll even say that even more verbosely. We might say, and now I'm going to do a proof by induction. And then at the end we might say, and now I'm done a proof by induction. And actually verbally say that to our reader. Again, why would we insert that? It's more helpful to our reader, whoever we're trying to convince with this proof. They'll follow along a little bit easier if we point these waypoints out as we go. Okay, so this is our first proof. Let's look at it in a little bit more detail. Oh, last bit, I guess. This is our first example of, I guess it's not our first example of a proof. We did a couple earlier when we were talking about sets. But this is our first example in this video. And so I'm going to call this an informal proof. What makes it informal is that we're not formalizing it down all the way down to symbols. Okay, we could formalize this all the way down to symbols. For most purposes in most of the world, we don't formalize down to symbols. We stay with informal proofs because luckily we're all equipped with pretty good internal logical computers. Okay, so we'll use those instead to translate this and test to see if it's correct. Okay, so let's continue with a couple more definitions. I promised you a lot of definitions in this video. So the next one here is a definition of what is a premise. So what is a premise? So we've sort of implied that earlier. A premise is a proposition that is assumed to be true prior to our proof. Now, often our premises can come in a number of different forms. I've mentioned a couple of them already, but let's go through a couple of them. An axiom, a theorem, or a hypothesis. So an axiom, this plays a very privileged role in a lot of logical arguments. An axiom is something that we assume to be true without any proof whatsoever. And so we often take axioms to be what we might call the common ground. So maybe we're trying to prove someone who is a skeptic, who is doubting us, but we have to have some common ground, some starting location where you agree that some proposition is true with me, and that is our common ground that we can use to build proofs upon. And so often axioms are going to be among that common ground. So again, maybe we want to start talking about number theory. Maybe we are, modern humans who've taken some college classes. So we can start with some common ground about there are natural numbers, there are integers, there are certain kinds of integers called prime numbers, there are divisors, there are a bunch of things that we can take as our common ground before we even get started. So we don't have to argue about those things. We don't have to worry about those things. And then often what happens is maybe someone comes in, a true skeptic, and says, I don't believe integers really exist. Then we back it up and we say, okay, but what do you believe exists? Do you believe natural numbers exist? And if they say yes, we say, okay, that's our common ground. Now we'll try and prove to you that integers exist and get you back up to the stage where we are so we can go on about our whatever we were trying to do with our integers. So these are axioms. So we have axioms of set theory, we have axioms of number theory, and then we have axioms of all other kinds of theories, maybe axioms of graph theory or axioms of string theory and so on. So there's all these different kinds of axioms that we might want to assume true when we are engaging in some logical enterprise. Okay, now the one type of axiom that we are going to emphasize a lot are definitions. That definitions, we just take them to be true, and part of the reason why we take a definition to be an axiom is there's just really no reason to question it. All we're doing is defining a term, the way that we're going to use a notation. And so since these are just conventions, we're really just trying to agree on a way to communicate with one another. So definitions usually are assumed to be true without question because there's no really good reason to question them. Okay, a theorem I've mentioned a little bit already. A theorem is something we're trying to prove true, usually, or it's something that we've already proven true. So often also part of the common ground that we might take to be true before we try and make our proof, that is other premises, might just be other theorems that we've proven earlier. Okay, and again, we might, if we have a skeptic or a student in our room who says, hey, I don't know that theorem, I don't understand how it works, that's when we say, okay, let's break it back down to the common ground we have. Let's go bring out the proof of this theorem and let's see if we can understand the proof together. And then once we do, we'll say, okay, now we can accept that this theorem is also true, and we can use that as part of our premises to start off our proof, the proof in question. Okay, and then the final piece that we have as a possible premise, there may be others, but these are the three ones that came to mind for me. A hypothesis is usually something that we're going to be assuming true, but unlike sort of the axiom, which there's no real good reason to question it, or a theorem where maybe there is good reason to question it, but we have a proof to tell you that it's true, a hypothesis is one that we might be assuming true just for the sake of an argument. Okay, and so it might actually be false. Why would we do that then? Well, there's a couple reasons. One is we might want to know what kind of conclusions might happen if we assume something to be true. Sometimes, assume that the universe is only 14 days old. That seems to be false. I'm a little older than that, so hopefully that's false. But then what could I prove true about that, or what could I use that theorem to prove true? I might be able to prove that I'm not 42 years old. That might be helpful, because if the universe is only 14 days old, then I can't be 42 years old. I must be at most 14 days old. Now, of course, that's a false thing. Now, why would that be interesting? I don't know. Maybe on the weekend you're sitting around and you're having a hypothetical philosophical conversation with your friends, and you might think, what would happen if the universe was only 14 days old? And that might be interesting. Well, there are other reasons we might take a hypothesis just for the sake of argument. One is maybe it's something we truly believe to be true. We believe it without a proof, but we truly believe it to be true based on for some other reasons. There's other reasons why you might believe something to be true other than a mathematical proof. And so if you believe it to be true other than seeing a proof, you might say, well, I believe this to be true, then what other things are true based off of that? And in math even, so this might occur outside of math, but in math there are a couple conjectures is often what we call them, or hypotheses, just as we're talking about here, which are statements that maybe within the realm of mathematicians, we're all pretty confident that this is a true proposition, but none of us have been clever enough yet to prove it's true. So, you can imagine us all sort of sitting around patting each other on the back saying, this is true, right? Yeah, that's true. Yeah, I agree, that's true. But none of us have been able to prove it true yet. And these are suspicious statements, because if no one's been able to prove it, then there might be a good reason for that. And a good reason for that might be that it's not true at all. It might just be false. Okay. And there are a couple such conjectures. I'll maybe name a couple so that you might know one or two. One of them is called the Riemann hypothesis. And the Riemann hypothesis is sort of a very famous mathematical hypothesis that has yet to be proven true. And if it is true, then a number of interesting other mathematical theorems become true automatically. And so this is sort of an interesting theorem, an interesting hypothesis, I guess you could say, that is like a keystone. It's sort of holding, or maybe a keystone's not the right analogy. It's sort of like a plug in a dam holding back these flood waters, that if someone is able to prove it true, it would pull out the plug and all these other truths would come flowing out as well, things that we've already proven based on this hypothesis. But no one's been able to prove that one last little piece yet. So if someone can go and put that last little piece in the puzzle, then the whole thing comes together. So the Riemann hypothesis is one that maybe one of you will one day prove true, if you do, or maybe one day prove the negative result, that is that there is no way to prove it true, or that it is indeed false. There have been other conjectures like this in the past. And if you take a look at some of my other videos, I talk about some of them, specifically when I talk about complexity theory and the complexity classes P and NP. But another one that might be of relevance to mathematicians and to those of you thinking about discrete math is something called Fermat's last theorem. Fermat's last theorem, Fermat was a famous mathematician, and he had sort of somewhat famously written a theorem in the margin of a book he was reading, I believe, a math book that he was reading. He said, "Oh, I've got this theorem, this proposition is true," and I think he sort of flippantly wrote, "I've got this elegant proof, but it doesn't fit in the margin here, so I'll leave it to another time." And of course, he died without sharing that proof. And so, when someone says something like that, that's usually a challenge out to the community. Okay, well, I'm going to come up with this proof. I'm sure I'm as brilliant as Fermat. Well, he was a pretty brilliant guy, so maybe he had a proof. There are many mathematicians today that would say, "Oh, well, we don't think he actually had a proof. We think he probably was mistaken. He probably had a very elegant false proof." And this is just a lot of pride out of us mathematicians saying, if we haven't found an elegant proof yet, then there must not have been one that Fermat had found. Well, that's fine. But it has turned out that Fermat's last theorem has been proven to be true. I think it was in the 80s. So here I am, my brain, my logical computer is maybe failing me here. But this was indeed proven. I think to prove it was a very long proof, and it involved some mathematics that was not available to Fermat in his time. This is another reason why some mathematicians think he probably didn't come up with an actual proof. But I am more willing to believe, I don't have a proof that he proved it, but I have reason to believe that he did prove it. So I do believe that Fermat had an elegant proof that we still haven't discovered yet today, and maybe there is one out there that you can discover and maybe popularize yourself. Now this is maybe bringing up another important point about proofs, is that for any particular theorem, there can be more than one proof of that theorem. And then the point that Fermat was making, he said an elegant proof. Elegance is sort of this property of proofs that's really hard to define. Usually it involves a couple of important properties: conciseness, smallness, preciseness, so not too much other flowery stuff in the proof that doesn't need to be there, but also easiness to understand is an important part of an elegant proof. So all of these things together might make the proof elegant. And so all of these different properties are important properties of a proof. Okay, so all of that was a little aside on the idea of hypothesis, but let's continue then. All right, there are a couple different kinds of proof. We've already sort of hinted at this. There's the formal and informal varieties that we've been looking at. Well, another variety we could look at is called a direct proof or an indirect proof. Now, what we've been focusing on so far have been direct proofs, informal proofs, direct proofs. And most proofs are of this form, both informal and direct. Direct proofs establish the conclusion directly from the premises in the way that we have just seen. The alternative is what we might call an indirect proof, where there are, again, maybe one or two different variants of indirect proof, where instead of trying to prove the proposition itself, maybe we try and prove an alternative proposition, or maybe we use an indirect strategy like a proof by contradiction, all of which I will talk more about in this video or in a future video. So when we're talking about a direct proof, where we're going to start from our set of premises, we can formalize this and say, use our formal propositional logic here and our set theory that we've built up in our previous couple of videos to say that we've got this set here P consisting of a number of propositions, P1, P2, up to Pn, which we'll say are also premises. So we will assume that these are going to be true. Let's also give the conclusion a name. We'll call it C. Then when we're creating a direct proof, what we're trying to do is we're trying to prove this conditional statement. So a conditional statement, conditional, remember, is another name for an if-then. So a conditional statement here where we're saying if all of the premises are true, if P1 and P2 and P3, etc., and Pn are true, then the conclusion is true as well. C is true as well. So this is, again, the base of almost all of the proofs that we do. Certainly every direct proof is a proof where we're going to have a collection or a set of premises. We're going to try and argue that if they are true, then the conclusion is true. Okay, and that's the validity part. Remember that if the premises are true, then the conclusion is true. So we're trying to establish the validity of our argument here. So let's again sort of flesh that out here. So in our direct proof, the strategy that we use if we're trying to prove this if-then statement is we start with the assumption that the premises are all true. Remember, given that we maybe do not know that, if our argument is also sound, then all the premises are true. Okay, but we might not know that's true. So in the way that we're going to make our argument, the way we're going to make our proof, is we're going to start with the premises assuming that they are true, and then arguing through valid rules of inference to the conclusion. That's what we want to argue. So we're going to start with the premises assuming they're true, and then argue, that's where the argument, the proof's coming in, that the consequent is true as well. Okay, so I've been hinting at this. So I say if we want to make sure that our proof is valid, then we must always use these valid rules of inference. Okay, so how do we use valid rules of inference, or what are the valid rules of inference? We'll take a look at those, but before we do that, I want to flesh out our proof that we've looked at in a little more detail. So let's look at definitions a little closer here. I said I was going to take a closer look. Now in a definition, usually what we're doing is we're setting up a relationship between a term and a property. So here I'm saying we're establishing a relation. So mathematically we might formally think of this as a relation, but we're also logically we call it a biconditional relationship where the truth of one end depends on the truth of the other end. We call this an if and only if. So in the definitions that I've presented and that I will present to you, I'm going to try and stress the if and only if relationship, putting the term on one side and the property on the other. So here I've called the term t, and then on the other side I've called this thing that's a property, I've called it p of x. It's sort of like a function here, but in logic we usually call these predicates. Okay, so this is a predicate, and where x here is a variable of some kind where we can plug in different things. Okay, so here we take this formalism to express the phrase x has property p, whatever property p might be. Okay, so when we have a definition, usually what we're doing is we're defining a term, what the term might be, and we're relating it to some property, that property that has to be true for the term to apply. So every definition should be of this form. And x is a t, if and only if p of x, where again we read this to be x has property p. So an x is a t if and only if x has property p. So again, just sets up a relationship between the term t and the property p. So here's an example definition. Here we're going to be defining the term an even natural number. So here we're saying a number x is an even natural number. And now we've got our if and only if, to relate the term to the property. And now the property that we have here is that x, the number, can be written as follows. It can be equal to 2 times k, where k is a natural number. So here an even natural number is such that it can be written in this form. This is the property p of x that we're relating to the term even natural number. And now what this allows us to do is establish a biconditional of both directions. That is, we can apply this, and I'll sort of mention this in more detail, and we can apply this in a proof in 2 ways. So a biconditional, the by part in the biconditional is saying that there's two directions on this conditional. It goes both directions, meaning if x is a t, then the property p applies to x, but also the other way around. If the property applies to x, then it is a t. Okay, so let's think of this with our example definition here. So a number is even if it can be written this way, but also if the number can be written this way, it's even. We know it's even. It goes both directions. So what that allows us to do in logic when we have definitions, and why we use them a lot as a primary tool, is that we'll usually be on one or the other end of this, and where we need to go is on the other end. So maybe we might assume we have an even natural number. Okay, well, what do we need, what are we going to use that for? Well, probably the next step is, well, what do we know about an even natural number? Oh, we can write it like this, and maybe this form is going to help us do some algebra or whatever the next step in our proof is. Okay, or vice versa, maybe we're trying to prove that a number is even. So if we can show that it can be written in this form, then the definition of even will allow us to conclude that the number is even. So the definition establishes two directions. If we're on one end of this bridge, we can cross to the other, or vice versa. And that's, again, why definitions are very useful tools. Okay, so again, this is what a standard definition is going to look like, and I'm going to try and structure my definitions to follow this structure, even if it doesn't, naturally feel that way. This is maybe another form of logic ease, okay, where I'm trying to structure things to emphasize the logic built into the propositions or the statements. Okay, so I now want to take that proof we started out with, the proof about the conclusion will be true if the argument is both valid and sound. We're going to formalize this using some of the mathematical or logical formalism that we had introduced in the earlier video. So here I'm going to start giving names to a couple different propositions. So here I have a proposition, and here I've broken down, I've sort of, don't really expect that this is something you do naturally on your first attempt. Usually you have to go back to your proof and sort of go through it with a fine-tooth comb and decide, well, what are the atomic propositions I want to bring out here? Now, I want to stress this word atomic. Now, atomic means it cannot be broken down any further. At least that's the meaning of the word that we use today. So that if you have an atom in this sense, is going to be a proposition that if we were to split it up anymore, it ceases to be a proposition. That's not always going to be true. We might choose a sentence to be an atomic sentence when it is really a more complicated sentence. That might be true here as well. That might be if there's no need to break it down any further, then we've broken it down. Now the atomic sentences that I've chosen here are fairly atomic. They can't be broken further without making them not propositions. So this first one is the argument is valid. Notice it has a subject and a predicate, meaning that it forms a true sentence, which means it expresses an assertion or a proposition that could be true or false. Splitting off either of those components is going to make it an incomplete sentence, and so it will no longer express a proposition. So it's definitely atomic, and the rest follow the same form, and we've just given them names. So let's just go through. So V is going to be the argument is valid, and S will be the argument is sound. Okay, those were obviously two components to the argument that we were making and the theorem that we stated. P is going to be the proposition the premises are true, and C is going to be the proposition the conclusion is true. Okay, so now that we have these symbols, we can take some of the phrases that we use and the definitions that we used earlier and codify them, that is, formalize them into these, using propositional logic, into these atomic propositions that we've selected. So let's try that. Let's start with our first one here. Remember our definition of a valid argument. An argument is valid. Notice that's one of our atomic sentences here. If and only if the conclusion is true when the premises are true. Okay, so we're going to have to break this all down. There's a little foreshadowing here, but we're going to break this all down. We already recognize this chunk. Argument is valid. That was this V. And since we just looked at what a definition is, a definition relates a term to a property. This is the term, or this is the phrase that we're trying to define, what an argument is valid means. So that proposition is V. So that's the left-hand side of my if and only if. V, an argument is valid, if and only if, whatever the rest of this sentence is saying. So what does the rest of it say? It says, the conclusion is true when the premises are true. Now remember how when we made this argument earlier, we flipped this around? We ended up saying that the when here, which we could also stress more by saying only when, can be turned around and turned into an if-then. Okay? Except the turning around part means we have to take the second bit of the second clause or the second phrase here and put it out front. So the second phrase is the premises are true. So what this really meant to us was if the premises are true, then the conclusion is true. So we have those here. P is the premises are true, C is the conclusion is true. And then we write that again with formal logic here. If P, then C. And I've put the brackets here to stress that the if and only if is relating this whole conditional to V. Okay? All right. So that was one definition. Let's see. This was actually probably the harder of the two, because it had this conditional as part of the definition. But our second definition here relating to soundness of an argument, so remember here, S was the proposition that the argument is sound, so that's our left-hand side. Well, an argument is sound if the premises are true. That was the definition, and remember it's an if and only if, so it's biconditional, goes the other way as well. So that's a pretty simple if and only if relationship set up here. S, if and only if P. Okay, P, the premises are true. So again, we're codifying these definitions. All right, so then the theorem that we were trying to prove said, if the argument is valid and sound, then the conclusion is true. So how do we put that together again? The if-then part is this if-then, and the end was the conclusion is true, so the then C part, maybe that's easier to see. But the first part, we can see has an and in it, because we have if the argument is both is just a word we use to emphasize an and coming up. Okay, so if the argument is both valid and sound, so valid and sound, again in brackets, then the conclusion is true. Okay, so if they're both valid and sound, then the conclusion is true. Now this is the statement that we're trying to prove true. Now remember, we just took a look at what a direct proof was. A direct proof was going to take some set of premises and argue that it's true. Now here we've emphasized two pieces, and there's a convention here. We didn't say if an argument is defined in this way, and if an argument is valid is defined in this way, and if an argument is sound is defined in this way, and if the argument is valid and sound, then we don't usually list all the all the definitions in our set of premises ahead of time, because that gets tedious. Frankly, it's just tedious. So instead, we usually limit our listing here to only a hypothesis that might need to be relevant. So here, we're going to assume our argument is both valid and sound, and that's what we need to argue that our conclusion is true. Okay. So remember, in our direct proof, what that means is we're going to have to start by assuming these parts are true, as well as our definitions, but no one's questioning that. So we'll assume that these are true and try and argue, and we'll see here in a second using these rules of inference to get to C. So let's try this. So we start out here assuming that V and S, so remember our phrase of the way we phrased this, we just said assume our argument is both valid and sound to let our antecedent be true, so we can begin our argument towards the consequent, the conclusion is true. So we'll assume V and S, and here I'm trying to emphasize the rule that I'm using to make this step in my proof. In a formal proof, we have to state the rule that we use at each stage. Okay, so here I'm saying assume V and S. This is what the rule that I'm following here is called hypothesis. Now the hypothesis is saying you can make any assumption you want as a hypothesis, but it might not be true. So the validity and the soundness rather of my argument here depends on the truth of this statement. If the statement is not true, then everything else here doesn't matter. If the statement is true because it's a hypothesis, then then the conclusion will follow. So this is a dependent clause. I haven't justified this yet. Okay, next step. Well, I've assumed this as a hypothesis, so now that I've assumed it, I can work with it. So what I'm going to do here is using a rule called conjunctive simplification. This is a very simple rule. I'll talk more about it in a second, but it's just saying that if you've got V and S, you can conclude V, and you can conclude S separately. So we're basically just splitting the AND into two separate propositions, V, and then separately also S. Now, why might I want to do that is because we've got this nice biconditional here saying that if V is true, then if P, then C is true. So the next conclusion or the next step in my argument, I'm going to now say, hey, since I know that V is true, I'm going to apply this rule called modus ponens, or we might say we could apply this definition, and we're going to get P implies C. We're going to do this one more time. Since our argument is sound, I'm going to apply it to this definition. Since S, remember I can cross this bridge. If I'm on one side, I can cross to the other. So I know S, therefore I know P. And now we're going to do that again. This is another bridge I can cross, this if and only, or this if then. But it can only go one direction. That is, if I'm on this side, I can go to the other. I am on that side. I have a P, so I can get to the C, therefore C. And the rule that I'm following here, I've emphasized it 3 times here, using the Greek name, is called modus ponens. Okay. So now I've taken that informal proof that we started out with here, and I formalized it, codified it in propositional logic. All right, so I mentioned in a argument, in a proof like that, we can only ever follow the rules of inference that are valid, and these are a list of the valid ones. They're not the only ones. You could probably come up with more, generalize some of these and so on, but these are the main valid ones that we might use. And there are others that are also not valid or invalid, and those we call fallacies, and sometimes we might highlight 1 or 2 of those, and maybe I will stress 1 or 2 as we make some of these proofs. But I do want to go through each of these rules of inference one at a time and try and engage your own internal logical computer and see if it makes sense to you, because I hope it does. Okay, most of these you should say, oh yeah, that's logical, that's reasonable, that's what we should think, because that's how our brains already work. Okay, so the first one we had here was modus ponens. Okay, Greek name. Maybe it would be better if we had got an English name for it, but it's too late for me. I learned this when I was 20, and now it's stuck in my head. Modus ponens. So modus ponens is this rule here, where we have 2 premises. So first I'm going to maybe talk about this notation that I have here. It looks like we're doing a sort of arithmetic. We're adding some numbers together or multiplying or something here. Well, here what we're doing is sort of logical arithmetic, if you will. Where up at the top what we have are listed are our premises, and then below the line we have the conclusion. This little 3 dots here means therefore. So we're saying what conclusion we can draw here, therefore Q. So this argument says if we know if P then Q, and we know P, then we know Q. And hopefully, for most of this makes sense. So if it's sunny outside, then we're going to go for a picnic. It is sunny outside, so hopefully the conclusion we can all draw is, well, therefore we're going for a picnic. That sort of makes, hopefully, logical sense. If not, then maybe you've got a logical switch flipped in your mind, and you should go work that out. Okay, hopefully all of us are saying, yeah, that's sort of pretty straightforward. Now, there is a fallacy that is very, very close by this one, and so I want to stress this one. If P then Q, Q, therefore P. Okay, so let's go through that one more time. If, I'm going to use my example again. If it's sunny outside, then we'll go for a picnic. We've gone for a picnic, therefore it must be sunny outside. Now some of us might be saying, yeah, that makes sense. And if you do, you're not broken, if that makes sense. Okay? Because even though this is a fallacy, that is incorrect logic. Now why is it incorrect logic? Well, the sentence, if it is sunny outside, then we will go for a picnic, says something about the state of it being sunny outside, but it doesn't say anything about the state of it being not sunny outside. What it's saying is, if it's sunny outside, then we go for a picnic, but if it's not sunny outside, whatever goes. We might go or we might not. Okay? So, if we've gone for a picnic, we can't conclude that it was sunny outside. It may have been raining, and we still just decided, oh well, who cares if it's raining, let's go anyways. Okay? We got to go see Granny or something like that, right? But if it's sunny outside, we know we have to go. So that leads us to the modus tollens, which is the next rule, which I think is really important, which is why the fallacy tricks us up sometimes. The modus tollens says if we didn't go for a picnic, then it must not have been sunny, because what we said was if it was sunny outside, then we went for a picnic. So what does that tell us? Remember, it told us that if it was sunny, we had to go for a picnic. So if we didn't go for a picnic, it must not have been sunny. Okay, the only way we could not go to the picnic is if it was not sunny. The way we could go to the picnic is if it was sunny or not sunny. Okay, so again, it's a rule that I think our brains are very in tune to naturally performing these types of reasoning. Okay, now I've got another column here that I've sort of just not mentioned yet, so maybe I should mention it. This column is called the tautology column. So for each of our rules of inference, here I've got the rule that is in sort of argument form with premise, then conclusion. Well, we can always write these in sort of the direct proof format that we had before. The P1 and P2 and P3 up to Pn implies the conclusion C here, where I've just got the premise, the first premise, and the second premise, and however many premises I need, all together in brackets, if, and then the conclusion here, the Q. And what this means is this sentence, and here's a great practice for your truth tables, if you want to practice your truth tables, grab any one of these sentences over here, make the truth table for it, and it should be trues all the way down, okay, of the final bit. Obviously you're going to break it down, but for the whole sentence it should be true all the way down. And what does true all the way down mean? It means tautology, okay, it means a tautology. So remember, tautology means always true. Okay, so again, just applying a definition, crossing the bridge back and forth there. Okay, so we've got our first two rules, hopefully make sense in our mind, and I've pointed out one fallacy. Okay, one fallacy that is not a valid rule of inference. But let's keep going. The next one, hypothetical syllogism. It's sort of just a fancy word for a very simple concept. If P then Q, and if Q then R, then if P then R. The idea here is that these conditionals sort of work like cause and effect. So I think of this as sort of like a string of dominoes. Each one of these sets up, if this is true, then this is true, and if that is true, then the next is true, and if that is true, then the next is true, and so on. So if you flick down the first domino, then all the dominoes are going to fall. All of them will fall. Or what hypothetical syllogism is saying is you can jump right to the end. If the first domino fell, then the last domino falls as well. Okay, and so this is an example of it with just two if-thens, P then Q then Q then R, but we could add R then S then S then T then U, and so on, as many as we need, and we can jump from the first one right to the last one with a generalization here. Okay, so this is a cool, important rule that we also probably follow. Okay, maybe something like, if it's sunny outside, then I don't have to work, and if I don't have to work, then I'll go for a picnic, and that's sort of our hypothetical syllogism. Since it's sunny outside, it means we're going for our picnic. Okay. A disjunctive syllogism, another one that your internal brain does all the time. P or Q, not Q, therefore, well, I just messed that up verbally, didn't I? So let's go try that one more time. P or Q, not P, therefore Q. The same is true backwards. So let's try the backwards version as well. P or Q, not Q, therefore P. Basically, what are we getting here? Well, P or Q is saying one or the other of these has to be true, possibly both. Remember, possibly both. This is inclusive or. But what that's saying, where the logic kicks in, is saying if one or the other of these has to be true, and we know one of them is false, then we know the other is true. Okay, does this work if we know one is true? Not necessarily. If we know that one or the other of these has to be true, and we know one is true, we don't know anything about the other one. We don't know if it's true or false. It could be true or false. Now, if this was an exclusive or instead of an inclusive or, there's an extra rule there we could use there. One or the other has to be true. If we know one of them, we know the other one. Okay, like in if and only if. It's a bridge we can cross both ways, but we negate it. We negate the value as we cross the bridge. That's what the XOR is. Okay, but this is not an XOR. This disjunctive syllogism here is with the inclusive or. If we negate one of the propositions, then the other one must be true. Okay, the next one is has to do with or as well. It's very simple. It's called addition. It's just if there's something that we already know is true, we can or anything else onto it and it will still be true. So let's pick something that we know is true. Snow is white. Okay, that's a classic proposition that we just assume everyone's gonna just believe is true. So let's just believe it's true. Snow is white. So that'll be our P. Okay. Now let's pick any Q that we want. That's weird. I don't know. I have a pet unicorn. Okay. Well, the statement snow is white or I have a pet unicorn is still true in virtue of the fact that snow is white is true. It has nothing to do with the I have a pet unicorn bit. That part's obviously false. But because we had a true statement to start out with, we could add onto it any number of weird propositions after it. I have a pet unicorn and a pet dragon, and I flew here from LA earlier this morning, and all these other strange propositions. None of them would have to be true. The whole thing would still be true. A little bit weird, not one we use as much. Okay, not one I think logically we use as often. Not one that I think helps us reason very often informally, but might be a rule that we have to use formally to get where we're trying to go. Okay, these two have to do with ands, and they do make a little bit more sense. The first one we actually used in our argument, which was we had a P and Q. It was slightly different. It was like a V and S or P and S or something like that. But this P and Q, the way we can simplify a conjunction, something that said, maybe this is snow is white and grass is green. Well, that affirms two things. It tells us snow is white and grass is green. I put the big gap in there to make them sound like they're two different sentences instead of one sentence with the and in there. Okay, so when we have a long conjunction of all ands, we can use that to break that down into each of its component pieces. Okay, we call that simplification. Well, again, we can do that kind of the other direction too, which is we can say if we know P is true, and then independently we also know that Q is true, then we can put them together and say P and Q. And that's just called conjunction after the and. That's what we also call this symbol or this logical connective. Okay, the last one here is a little bit weird. Okay, and that's because this one, again, I don't think we use very much naturally. Our natural logical computers don't use it very much. But our artificial logical computers, meaning computers, use it all the time. That is, if a computer is trying to do logic, it uses this rule called resolution. And one of the reasons why it uses it, and we sort of hinted at this earlier about universal sets, is if if we have our logic in a certain form, this is the only rule we need, resolution. We could do all our logic by just using resolution. Now, normally our brains don't want to put things in this form and don't usually keep logical sentences in this form, so it's not useful for humans. It is useful for machines, for computers though. Okay, but let's look at this last logical rule, again called resolution. We have here two disjunctions, two ORs, P or Q, and then not P or R. Now the important thing here, okay, is that we've got the P here is being negated by the not P in the other clause. Okay, we sometimes call these clauses, but I've been calling them premises, so let's call them premises. So in the other premise, we've negated that same term. And then these other twos, the Q and the R, doesn't really matter what they are, so that's why we've called them Q and R, made them different. Okay. Now, the conclusion of this is we can just conclude Q or R. Okay, now let's see if we can reason this through ourselves and see why the computer uses this rule, or at least that this rule is true. Okay, so here I want to consider maybe a couple possibilities of our state for P. Okay, noting that P could either be true or false. And if it is true or false, it ends up making one of these terms true. Okay, so for instance, let's just assume P is true for a moment. If P is true, then the or Q means that this whole thing is true. But then this term becomes false, and this one simplifies to just R. Okay, now that was one of our possibilities. So let's sort of break our two possibilities down and be very explicit about it. We are considering cases of the value P. P could either be true or it can be false. And we just considered what happens if P is true. If P is true, we decided this whole term becomes true, so we don't learn anything about Q. But this term becomes false, and using our disjunctive syllogism here, that means the R must be true. Okay, so in the case where P is true, R must be true. Let's do the other case now. The other case is when P is false. When P is false, this term, this not P, becomes true, and we learn nothing about R. But this, since P is false, this becomes false, and then using our disjunctive syllogism, or just simplifying using our logical symbols from before, we get down to Q. So we know we have Q. Now remember, to start off this we had two possibilities. P was true, or, I'm emphasizing here, or P was false. In the case where P was true, we got R. In the case where P was false, we got Q. And we said we had one or the other, so the conclusion we get to here is Q or R. One of these two has to be true. Maybe both, but one of these two has to be true if both of these statements above here are true. Okay, now this is kind of a weird one again. We probably don't use this as much. I'm not sure. Maybe we do. Maybe there's an example of a natural reasoning situation where we would do this. But I don't know of one off the top of my head. So if you have one, feel free to let me know what you think would be a good example of this. But this does factor into computer logic a lot. Okay, in particular statements algorithms to see if a statement is satisfiable or not. Satisfiable meaning to be made true. Okay, so these are the rules of inference. The rules of inference you're going to want to use when you are performing logic that is maybe authoring a proof of your own are these ones, because these are the valid ones. And you don't want to step outside of this set, because even if it feels logical to you, it might be one of the fallacies. A fallacy is something that feels logical but really isn't. Okay, and then I will mention that if you are going to be using these, if you're formalizing your logic, you might be using all of these except for possibly resolution. But if you're doing it informally, we tend to stick to some of these natural ones. I'm going to say modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism. These are all very commonly performed. I would say we do conjunctive simplification and conjunction, but we do these ones so naturally that they're sort of invisible to us. They only happen behind the scenes. Our brain doesn't even let us know that we're doing them. Whereas these ones, we might be aware that we're going through these steps as we do them. Okay, so again, these are the rules of inference we want to use in our proofs. Now, just to remind ourselves, we're going to be using proofs for the rest of this series of videos. So we might be coming back here more than once, but also these, like I said, our internal computer is pretty good at performing these. So we already have been exercising these tools for many, many years as we've been learning about all kinds of things. And so here we're just trying to take, again, those implicit tools that we're already pretty good at and making them explicit, becoming professionals, if you will, at using logic. Okay, so I just sort of want to conclude this video, which has got a little bit long, with just a description or a discussion of a couple or of theorems and a couple different names that we can give for theorems. So theorems, as we've already said, are sort of propositions that we have proven true, or maybe we plan to prove true, but there are sort of other names that we sometimes give to theorems or theorem-like entities, usually depending on our purposes, what we plan to use them for, what we have used them for, and so on, or maybe how we've proven them. So the first one here is just the theorem. That's our standard use, propositions that have been proven true or that we are about to prove true. So we've already used that one quite a bit. Another one that we've encountered was hypothesis, but I just want to stress here that we also regularly use the term conjecture if we want to stress that this is an unproven theorem or hypothesis. We will call it a conjecture sometimes. This is one that's not yet been proven true, and remember, we use these for a couple different reasons. Maybe for the purposes of argument, just for the sake of argument, we're going to assume something's true to see what happens. Or, like I mentioned with the Riemann hypothesis, maybe it's something that we believe to be true, we haven't got a proof yet, and we want to see what else would be true once a proof materializes down the road. We have reasonable faith that that proof would appear down the road. No actual proof yet, but we hope it's going to appear maybe, and so we might call that a conjecture. Another term I think we encountered briefly was called a corollary. A corollary is a theorem that usually kind of follows immediately from another theorem, or follows without having to apply too much additional logic, meaning that it seems obvious. We might sometimes call it trivial or obvious. Now sometimes, people will say a proof is obvious or trivial, like Fermat did, when it really isn't, and that's maybe being a little bit, pompous or proud. And so usually we reserve corollaries for very, very clear or obvious conclusions that are to be drawn. And even still, if you see a corollary and you say, hey, this isn't obvious to me, there should be no shame in that. What is obvious to one is not always obvious to another, and we all are established at different levels of mathematical maturity. So if you're learning some stuff, you see a corollary and you say, hey, that doesn't make sense to me, ask someone, and they might say, oh, and it's usually a 2 or 3 step proof that will probably be pretty easy to follow. Okay, the last one here on my list, at least, again, there might be more out there that I'm missing here, is called a lemma. A lemma is usually not as important. It's not something we're actually trying to prove, but it's kind of a stepping stone on the way there. Whatever we're trying to prove is complicated enough that we want to break it down into smaller pieces, proving each of the pieces one at a time. And each of those intermediary pieces is maybe not that interesting in itself. So we'll call each one of those a lemma 1, 2, and 3. And then often we'll say, okay, the theorem follows from lemma 1, 2, and 3, and maybe that might be as a corollary. Once we've established lemma 1, 2, and 3, it might just be immediately obvious that the theorem is also true. And maybe that's because, say, the definition we're trying to prove has 3 parts to it. Part 1, 2, and 3, and so we establish a lemma for part 1, part 2, and part 3, and then it just becomes obvious that the definition holds. Here I've got another example of when we might use lemmas, at least a very common place that we might use in the next series of videos, is if you're trying to prove a biconditional, Now definitions are like this, but we don't usually prove definitions, we just assume them. But say we have a biconditional we want to prove, P if and only if Q, then the standard technique to prove that is to break it into its two conditionals, its two components, if P then Q and if Q then P, and prove those separately. Okay, prove them separately and then use conjunction to just glue them back together again. All right, so this video is meant to be sort of an introduction. What is a proof? What are some of the parts of proofs, things we can expect when we encounter a proof? In my next video, I want to go through an example or two or three of proofs, and then starting with informal proofs and then formalize them in the way that we've done with our first proof in this video. So that will give us a little bit more practice with informal proofs and formal proofs. And then once we've had that practice, we're going to abandon formal proofs, mostly because they're very tedious. And when we want to start writing longer proofs, we don't want to spend that extra time doing all that tedious extra work. So once we're familiar with them, we will abandon them. So the next video will become more familiar, and after that, we will abandon them. All right, thanks a lot for watching, and I guess we'll see you in that next video.